3. Okay, now it's recording. Okay, so this is just a quick overview. I'm doing this for the recording. This is just a quick overview of what we're doing today. It's just talk about the history basics, and then we'll get on to binomial expansion, other uses for Pascal's triangle, and then some practice at the end. So this is, I'm not going to go over this because it's if you want to, we're going to share the slideshow later. So if you want to read this and like check out the credits and other things, then I'll let you guys check that out for yourself. But so Pascal's triangle is an organization of binomial coefficients in the form of a triangle. The numbers in Pascal's triangle are placed in such a way that every number is like the sum of the two numbers above it. So as you can see, like 2 is the sum of 1 and 1, 3 is the sum of 2 and 1. Yeah, it's like that for the entire triangle. So Pascal's triangle is mostly used in things like probability combinations and algebra. So there's a lot of like even though there's a lot of patterns in Pascal's triangle that most of them will be used, and Alan and Raymond will go over them later. Like some that I probably won't be mentioned, or like these are just some properties. These are the the diagonals of Pascal's triangles. The outer ones are all ones. These are all counting numbers. These are triangular numbers, and then these are all tetrahedral numbers. And then and then some of the other things are like every row this is considered row 0, and these are considered row 1, 2, 3. So you should remember that for the rest of the presentation. But each row, the digits are all actually represented by the powers of 11. So you notice that 1 is equal to 11 to the power of 0. 11 is the power to the 11 to the power of 1. 121 is 11 to the power of 2, and so on. So like 1,331, 14,641, and then so on. However, 11 to the power of 5 is it's not directly 1, 5, 10, 10, 5, 1. It's 1, 6. I think it's 1. Okay, yeah. Anyways, but this isn't the exact way to show 11 to the power of 5. Some of the numbers are combined together to form the entire number, but those are just some quick properties of Pascal's triangle. So generally, you can use Pascal's triangles to find coefficients of binomial expansion, which is the main thing we're going to be focusing on today, and then the probability of heads and tails and a toss of a coin, combinations, and then etc. So I'm going to let Raymond start the basics.
Okay, so oh wait, where did it go? Okay. So the Pascal's triangle consists of infinite rows. Each row consists one more element than the previous one. So I think Darwin mentioned this, but like the bottom the top two add to the bottom number. So for example, 1 plus 1 adds up to 2, so on. And the sum of each row is the next power of 2. So if you look, so 1 so to the 0th power is 1. 1 plus 1 equals 2. This is 4. And so on. So the sum of each row is just 2 times the row number. And if you remember, the first row is always row 0. So for example, let's say like row 10. Row 10 would be 1024. The sum would be 1024 because it's 2 to the 10th power. So, all right, let's do one problem first. So what is the sum of the
Why are you on a meeting? I'm just
what is the sum of the coefficients of x plus y to the 5th power? I think Alan's going to go more in depth in this later, but this is just going to be an introduction problem.
Also send your answer privately to Raymond.
Okay, so I got a few answers, so I'll just go ahead. So if you notice, the degree is to the 5th power. So you would use the 5th row of Pascal's triangle, and that would you can use the easy way, which is just finding the sum. And like I said on the previous slide, it would be 2 to the row number, which is 2 to the 5th power. Or you can write out the Pascal's triangle. So 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. And so those are just two ways you can do this problem. Let me close this. Okay. I think, yeah, this is another problem. This is basically just the same concept, but we're using it like differently. So I'll give you a minute to do this problem. Okay. So we can use like the last questions method. So wait, is my okay. So since the power is to the degree is to the 3rd power, then we can use the 3rd row of the Pascal's triangle. So that would be 1, 3, 3, 1. And you can write it out if you want, but you eventually find 1, 3, 3, 1. And this would be the coefficient of x to the 3rd power. This would be the coefficient of x squared y. This would be the coefficient of x y squared. This would be the coefficient of y cubed. So if you look at it, then it will just be 3. And if you don't understand this, that's fine. I think Alan's gonna do a more in-depth talk about this later. So let me just close this, and yeah, so I'm gonna let Alan do this part.
Yeah, before that, does anybody have any questions about the previous stuff?
Yeah, and if you don't want to speak up, then you can just private message the person who's teaching at the moment.
Okay, I'm gonna take that as a no. Here we go. All right, so wait. Yeah. So this is So the binomial theorem is wait, can everybody hear me? Wait, okay, yeah. The binomial theorem is a little faster than using FOIL to solve binomial expansions. The Pascal's triangle can make this a little easier, or just like general tricks for this. So if you have this expression, a plus b squared, it's easy to use FOIL, and at the end you'll get 1a squared plus 2ab plus 1b squared. And so if you look at the coefficients, it's 1, 2, and 1, and I'm pretty sure Raymond already stated this, but that's row 2 of Pascal's triangle, and that's because it's defined by the exponent that the binomial is 2, which is 2. And so, but we still haven't found the actual terms that the coefficients go in front of. So basically how it works is that the first variable, the first term, which is a in this case, will start at the highest exponent, which is defined by the the exponent of the binomial is 2, so it would be 2. So we start with a squared, and then it slowly decreases in each new term throughout the expanded expression. So it'll go down to a to the first power, and then it'll become a to the 0th power, which is just 1, and kind of just disappears. And it's the same with b, but b goes up to the highest exponent, so b starts with 0 and it simplifies to just 1, and then b goes up the first power right here, and then the second power. So that's a little trick that helps you find it easier instead of doing all the weird calculations. Oh wait. Oh shit. Okay, so sorry, so I accidentally went to the next slide, but it doesn't really matter the order. So this is the binomial theorem. So the binomial theorem is x plus y to the nth power equals n sigma k equals 0, n combination k times x to the n minus k power and y to the k power. So the x and the y represent the variables of the binomial. N is the degree, so the power. And then you have sigma, and if you don't know what sigma means, it basically means just like every number in between. So you would do this for this example, we have 4 as the degree. So you do it for 0, 1, 2, 3, and 4. And then you already know what n is, it's the degree, and then k would just increase. So if we look at this example, a plus b to the 4th, we have so we start, the first one would be n would be 4, and sorry about the bad drawing. N would be 4 and k would be 0, so n factorial over k factorial would be 4 factorial over 0 factorial, which would 0 factorial would just simplify to 1, and then you'd have 4 factorial, and that would just simplify to 1. So the coefficient of the first part, the first variable would be 1, and then you have a to the n minus k power, which is 4, and then b to the k power, which is 0. So your first term is, I'm gonna write it up here, is a to the 4th, and then wait, sorry, let me just, yeah. So your first term is a to the 4th, and then your second term, so it's the same process, but k goes up to 1 this time. So then you have 4 factorial over 1 factorial times 3 factorial, which is this simplifies to 4. So then you just have 4 x to the n minus k, so 4 minus 1, so x to the 3rd, and then you have y to the 1st, or I mean a to the 3rd and b to the 1st, because the k went up to 1. So your second term would be 4a to the 3rd and b to the 1st. So I'm not gonna do the whole thing because that'd take a while with all the drawing and stuff, but as you can see, so with the sigma, the k just increases, and you do it with 0, 1, 2, 3, 4, and eventually your end result, you'll just get a plus 4, a to the 4th plus 4a to the 3rd times b plus 6 a to the 2nd, b to the 2nd, plus 4. Here, let me move this. A, b to the 3rd, plus b to the 4th. And as you can see, the coefficients, we have 1, 4, 6, 4, 1, which corresponds to row 4 of Pascal's triangle defined by this degree. And then the terms, we use the rule, and as you can see, A goes down from 4 all the way to 0, and B goes from 0 all the way to 4. So yeah. Any questions?
A quick example with binomial theorem. So we're supposed to expand a plus b to the power of 3. Now, the answer is that instead, basically we're using since like Alan said, we're using the exponent of 3, which is the third row of Pascal's triangle, and this is just kind of the same problem that I think Raymond gave earlier in one of the introduction problems, but you basically have the coefficients of 1, 3, 3, 1 in Pascal's triangle third row. So then using the methods laid out in the previous slide, we started with the highest exponent 3 and b at the lowest, which is 0. So then the first term would be 1a to the a cubed. Then the second term would be 3a squared and b to the power 1. Term 3 would be 3a to the power 1 and b squared. And then term 4 is same thing as that, is 1b cubed. So altogether, you look at this, it's the same thing as before. It's just 1, 3, 3, 1 for the coefficients of these numbers. So Pascal's triangle connection. So if one were to use FOIL to expand this binomial, you would get something like a plus b times a squared plus 2ab plus b squared. I think everybody knows what FOIL is, but if you were to use, after you apply FOIL to this number, then you start multiplying the ins and outs of the two parentheses, and then you would get something like this. And then after you start adding likewise coefficients, then you would eventually result into something is the same thing as before, a 1, 3, 3, 1 as each of the coefficients. So to get from the first result to the end result, you simply add 2ab squared and ab to get 3ab squared, which is what's going on right here. And then the same with 3a squared b. You add the coefficients 1 and 2 to get 3 right here, which is also how you get 3 in row 3 on Pascal's triangle. Since you're adding the coefficients 1 and 2 here to 3ab squared, if you look at Pascal's triangle here, like the explanation for the properties of Pascal's triangle before, it's the same thing where the two numbers above a number add to the number below. So this case is 2 plus 1 equals 3.
So this same procedure will work with more complicated quantities. So let's say you have 2x plus y to the third. Well, so it's basically the same as like a plus b to the third or something like that, because you still have two terms, 2x and y, and you just do the same thing with them. So you start with the first variable, 2x, and you can plug it in with parentheses here. And so it'd be 2x to the third, because here, and so you put that, and then the coefficients will be 1, 3, 3, 1 with row 3 of Pascal's. And so when you substitute it in for parentheses, 2x to the third would be 8x to the third. And yeah, you also gotta remember to make sure you put the whole term into parentheses. Or you always use parentheses because, for example, let's say you had 2 times x to the third. Well, that one you get x to the third. Well, okay, that's a bad example, but basically you just always got to use parentheses in it. And I'll show you later on with negatives, that'll make sense. But so each of these terms, you take it to the exponent and then multiply by the coefficient. So 2x to the third is 8x to the third times 1 is 8x to the third, and then 2x squared. So the exponent of variable 1 goes down, and then term 2, the variable will go up, and you end up with this result. So it's a little more complicated, but it's still the same process. And for this other example, we have 1 plus b to the fourth. In this one, instead of a variable, we're now having an actual whole number. So in this one, you'll plug it in the same way, but you only have one variable, so it'll be a little simpler. And as you can see, the the second variable is just clearly going up 1, 2, 3, 4. And then again, the coefficients, this is row 4, so 1, 4, 6, 4, 1. And then, yeah, so if you have a whole number like 1, it'll be a lot easier to do the exponent. It'll just always be 1. So you'll just end up with 1 times whatever else there is, like 4p. So, but if you don't have 1, you just gotta be careful because those exponents can get really complicated. Yeah. So, next slide. All right. So let me move this back over here. So the terms in the binomial expression can also be negative. And remember, when you're raising a negative number to an even power, the result is going to be positive. And when raising a negative number to an odd power, the result is negative. So it takes 3a minus 2b to the 5th. So this one's a little bigger. So here, obviously, you substitute it in again, and it's row 5 of Pascal's, which is 1, 5, 10, 10, 5, 1. And yeah, so the numbers are a little bigger, and you'll have to do a little more math to get them. But for the looking at negative ones, when you substitute negative 2b in, and make sure to do negative 2b, not just 2b, you have negative 2b, you have to remember that you're putting the whole thing in parentheses. Because, like, for example, let's say you have negative 2b to the 4th power, parentheses, right? This one you get 16b to the 4th, because multiply both of those, or take both of those to the 4th power. But let's say, what if you have this? What if you have negative 2b to the 4th? Well, you might do the same thing, but look, it's or no, that's a bad example. Negative, and then parentheses 2b to the 4th. That you get 16b to the 4th the same way, but then you'd have a negative to add on. That wasn't part of that thing. So you need to make sure you put it in parentheses. So yeah, it's the same concept as if you negatives and stuff. Okay, yeah. So now let's do the other one. This one has fractions, and it's again the same way, but you just you gotta remember when you're taking a fraction to the exponent to an exponent, you multiply both sides. So you don't want to just do like 2 over x to the second, you just do like 4 over x. And these are gonna come out a little weird, but it's still the same concept again. The exponents are going up, and you make sure to do the exponent and then multiply by the coefficients according to Pascal's triangles row. Alrighty,
So, oh wait, no, you can see this. Oh no. Okay, so do either problems 4, 5, 7. Just choose one. Or you can do all 3 if you want to, but I don't think anyone wants to do that. Okay. Let's go to the next slide. Okay, so these are the answers. Let me just write the question first. So for number 4, it was 1. Oh wait. Okay, so it was 1 minus. Wait, Alan, is that right? That was the question, right?
it was the question.
Okay. So wait, was it? I don't think it.
I think the solution may have been wrong, but you can just, I
Okay.
think you just
Yeah, I'll just do it right now. So if it was 1 minus 5x to the 5th power, we can use the 5th row of Pascal's triangle. So, well, this is 0, 1, 1, 2, 3, 4, 5, 6. So this is the 5th row. So it's 1, 6, 15, 20, 15, 6, and 1. And you can find the coefficients using that. And just make sure to use negative 5x instead of like x, or like the coefficient you would regularly use. So this would just be 1 to the 5th power. this would be 1 to the 4th power times negative 5 x, and then so on. So I'm not going to do that, but yeah, you can see what it would look like. Okay. So number 5, what was the problem for number 5? Wait, Alan, can you tell me what the problem for number 5 was?
Yeah, number 5 was x plus 6 to the third.
X plus 6 to the 3rd power. Okay. So this would be, we can just use the 3rd row of Pascal's triangle, which would be 1, 3, 3, 1. So normally it would be like x to the 3rd power plus xy, x squared y plus xy squared plus y 3rd power. And we can use that and then just change it into x equals x and then 6 equals y. And you can plug that in and you can find the answer, which is x to the 3rd power plus 18x squared plus 108x plus 216. And for the 7th problem, I forgot to write all of these down. Alan, can you tell me what the 7th problem was?
Wait, is my mic still on?
Yeah.
Okay, 7th problem was 1 plus 3 over a to the 4th power.
Right, so you can just use the fourth row, which is 1, 2, 3, 1, 2, 3, 4, which is 1, 4, 6, 4, 1. And same thing, what we did for number 5, we can, normally it'll be like x to the 4th power plus x cubed y plus dot dot dot, right? And then plus y to the 4th power. And you just replace x to be 1 and then y to be 3 over a. And then if you solve that, you just get 1 plus 12 over a plus 54 over a squared plus 108 over a cubed plus 81 over a to the 4th power. Right. So
If you've noticed that if you look at most of these problems, they're all, the exponent are they're all like small numbers. They're all like to the power of 2 to the power of 3, and you could technically already just go to the line in Pascal's triangle and then just reference it, and then you would know how to solve the problem. But what if the exponent goes to something really large, like 14? So and this is when binomial theorem is going to help. So, as mentioned earlier, the binomial theorem is better used with higher exponents. Say if you want to find the first 3 terms of something like x plus y to the power of 19. So these are 2 more ways to express the binomial theorem. So this first one is basically the same thing that Alan was talking about with sigma.
Oh, sorry, I meant without sigma.
Without sigma? Yeah. Anyways, it basically shows the exact same steps, it just expands it with everything very specific. It makes everything very specific. So even though it's really long and it's really big and looks kind of confusing, it's actually not that hard to understand. And then the second one is where it's basically the same thing as this one, except one of the variables is replaced with the whole number 1, or any whole number really. So, and it does result in larger coefficients, but it has 1 less variable to deal with. So I suggest that you probably write this down, write one of these down.
And just to add one more thing, it looks confusing, but so basically you just have like n, and that's just say it's like 6. You continue this equation until it reaches like that number. And so for example, like the n times n minus 1, that's basically sigma, because when you think about like with the sigma form, it'd be like 8 factorial combination 2 factorial, but
Well, someone is the, I mean,
that'd just be 8 factorial or something like over 2 factorial, which would just times 6 factorial, which would actually just simplify to 8 times 7 over 2 factorial, which is what we're seeing here. And it's the same thing going down. So it's just without sigma. So if you understand sigma, that might make it easier to understand, but it's really just the same thing.
I just said that it just, this would just continue on for forever, depending on the amount of terms that you're working with. And then each time the factorial on the denominator increases by 1, you have another section of parentheses with n minus the next number and then x to the next exponent. So I'm gonna give I think there's 2 example problems that I'm gonna ask you to use one of these ways to solve instead of just referencing the Pascal triangle. So x plus 1 plus x to the power of 3. I know this problem has been presented like many times in the past of the slideshow by Alan or Raymond, but this time we're going to be using the binomial theorem to solve this instead of just referencing the Pascal's triangle. So I'll give you like a minute. Here's the solution. The solution is even though this is the third row of Pascal's triangle again, the coefficients being 1, 3, 3, and 1. This time we're using the binomial theorem to solve this. So as you can see, we're just analyzing the same things as before. So by plugging in the numbers, the exponent being 3, in this case, in the formula, this was the exponent would be n. So you plug in n in everything. So it would be 1 plus 3x plus 3 times parentheses 3 minus 1 over 2 factorial, and then x squared. And then you continue it again because in the third row of Pascal's triangle, there's 4 terms. And then it would be 3 times 3 minus 1 times 3 minus 2 parentheses over 3 factorial times x cubed. So after you solve all of these and divide by the factorials, you should get 1 plus 3x plus 3x squared plus x cubed. Coefficients are the same as the third row of Pascal's triangle, and this way you're just using a different way to solve it. Okay. So the next one. So this time we're going to be using it for what it's really useful for, which is finding terms when the exponent is a really large number. In this case, it's 1 plus x to the power of 32. So we'll probably give like 1 to 2 minutes to solve this using the binomial theorem. So I think it's been, I lost count, but I think that's a good amount of time. So this time we're looking for the first 3 terms of 1 plus x to the power of 32. All right, so this is when binomial theorem becomes useful. We're basically taking the numbers and just applying it to the binomial theorem. I only asked for the first 3 terms because if you were to find all the terms in the 32nd row of Pascal's triangle, that would take an incredibly long time. So the answer is 1 plus 32x plus 496x squared, because you're applying 32 to all the places where n is, and it stops here because this is the third term of the binomial theorem. So yeah, I think we're gonna do like 2 practice problems, and it's going to give you 3 minutes. And number 1 has 2 parts, A and B, so I'll give an answer for both of them. You can send them separately or together. Well, it depends on what Alan thinks. All right, so the 3 minutes is up, so I'm gonna explain the problems now. So the solutions to the previous slide. So remember, I'm gonna have to switch, go back and forth because I have to remember the problem. So the first one is to use the binomial theorem to expand a 1 plus x to the power of 4 and b 1 plus x to the power of 5. So if you notice that this is technically the same problem as before, where we reference Pascal's triangles, fourth and fifth rows. You can see 1, 4, 6, 4, 1, and then 1, 5, 10, 10, 5, 1. But by using binomial theorem, we're really just applying the same things as before. So like for a, it'd be 1 plus 4x plus sorry for the bad writing. 4 minus 1 over 2 factorial x squared. And then we would continue doing that for the other 4 terms until you reach the final one. So I'm not going to write out all of it because it's kind of excessive and repetitive, but it's that way. And it's the same thing you do for b, except this time it's just the extra term of the 5 terms. So yeah, that's number 1.
Oh yeah, I should have mentioned this before, but for number 2, you could have put like 2 to the 12th instead of like 4096.
Okay, and then number 2, yeah, like Alan said, the 12 is a big exponent, so that you only find the first 4 terms of the expansion of 2 plus x over 3 to the power of 12. And it's the same practice as before. We're using it's just this time there's a fraction in one of the coefficients, and the answer is 4096 plus 8192x plus 22,528 over 3 x squared, and then 112,640 over 27 or x cubed. And obviously this would go on, but it's already really, and the numbers are already really large, and it shouldn't be it shouldn't have, there's no reason really to continue. So I think next for Pascal's uses, it's for Alan's
Place. So here's some other uses for Pascal's triangle. So I'm going to put that at the top. Wait, okay, all right, yeah. Just keep that, okay. Use web paint. Here we go. Okay, so Fibonacci sequence is, I'm pretty sure you all know what this is, but just if you don't, it starts with 1 and then 1. Then the pattern is each subsequent number is the sum of the 2 numbers before. So 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, blah, 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 blah. So as you can see, each diagonal of Pascal's triangle adds to the next number in the Fibonacci sequence, or Fibonacci. I don't know how to pronounce it. So just like take any one of these, you get 4, 10, 6, 1, that's 21. And then, yeah, so these diagonals are a little weird, but as you can see, the next one will be 6, 35, 56, 36, 10. There's a little 1 down here, but you can't really see it. And it should add up to 144. And if we do that, we get 10 plus 36, 46 plus 56 is 102 plus 35, 137 plus 6 is 143, and then that 1 down there you can't see is 144. So yeah, the diagonals add up to that. And then next, we can talk about coin flips. Yay, nice transition. Oh yeah, so yeah, so for each, you probably know this already too, but for the coin flips, each the amount of times amount of coins that are flipped corresponds to the power of 2. So for example, if you flip it once, there's 2 to the 1 ways things you can get. So it's like heads, you can get tails, and for like 2 flips, there's 2 to the second, which is 4 different things you can get. And that's the same with Pascal's triangle with the sum of the rows. But as you can see, like here we have 1 and 1 for each different possibility. So there's heads and there's tails. Oh, oops, okay. But for 2 coin flips, there's 4 different possibilities, but for some reason you have a 2 here. And you might be thinking, oh, why don't you just have 1, 1, 1, 1? Because like there's 4 different things you can get, right? Well, no, because heads. Well, when you just look at these middle two, you see the one's heads tails and other's tails heads. They're rearranged differently, but there's still just one heads and one tails in it. So it's just rearranged in a different way. And then you can take 3. This 3, the second 3 corresponds to these 3 numbers. And they're all 2 heads and 1 tails. They're just rearranged in a different way. So yeah, that's kind of how coin flips relate to Pascal's triangle. Alrighty, next slide. Yay, this is probably the hardest one in the entire slideshow. Okay, so this is hockey stick identity. Okay, this is hockey stick identity. So basically what it states is that the sum of the elements in the diagonal line starting with 1 is equal to the next element down in the opposite diagonal direction. So you can see that 1 plus 3 plus 6 plus 10 plus 15 is 35. And then why not we can just take another random one, like let's say, well, as Darwin said, these are the counting numbers, but let's see 1 plus this, and then the next one will be in the opposite diagonal direction, which you get 21. Let's see, 1 plus 2, that's 3 plus 3 is 6, 4 plus 5 is 9, and another 6. 12 plus 9 is 21. So that does work for anyone. 1 plus 2 equals 3. 1 plus 5 plus 15, that's 21. So it works all over the place. But remember, it has to start with 1, and the end result will be in the opposite diagonal direction. Also, okay, so here's the formula. So for whole numbers n and r, n sigma k equals r, or just n sigma r, and then this combination, and then yeah, so we can look at this in example. So there's a lot of more complicated ways to do this, but that I think we have a few complicated versions of this in the practice, but right now we have this is just an easier one. So I'm gonna do this example. So Mabel is playing a carnival game in which she throws balls into a triangular array of cups. Okay, and she'll throw 3 balls, and she'll win the game if they're in a straight line, not necessarily adjacent and in different cups. So, like for example, like, these little things can be balls. That's in a straight line, and yeah. Disregarding the order the balls go into the cups, how many ways can she win the game? Okay, so let's use hockey stick to solve this. So the largest row you have is 6. So that n is gonna be like the I guess not really total, but like largest thing. So this is gonna be like the largest row you can get. So that would be 6. So you would have n equals 6. And you have 3 balls that go into this, or that are possible. So you have 3 balls. And that will be n equals 6 and r is 3, or r k. So k equals r equals 3. And so we can start making our equation. So we have that what was I gonna say? Okay, so 6 factorial over combination 3 factorial, but this equals n plus 1, r plus 1. So we end up with 7 factorial over 3 factorial over times 4 factorial, because it's a combination. So that ends up with 7 times 6 times 5, which is 210. And then 3 times 2, which is 6. And so you end up with 35. But now what do you do from here? Well, there's 3 sides that have 6. 1, 2, 3. It's a triangular array. And so you multiply this by 3. And so that would give you 105. But we're still not done. And so this is a mistake I made when I first did this question. But if you look, there's still one more way we can get question. So I mean get wins. So the way we've been doing this is when it's parallel to one of the sides. So like here, 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 it's parallel to the largest side using 3 balls, and that gives you 105 different options. But what if it's this 105 is parallel? What if you have a perpendicular one? So, for example, that would look like so like this. Oh. So wait, I got a perpendicular ones is so let me just erase this real quick. Okay, so we can put the balls in this way, and they're also straight line. And so there's 3 ways to get this on each side. These 2, and then this one in the middle. And that's 3 ways for each side. So 3 times 3 would be not oops. Okay, wait. 9 for the perpendicular, and for one parallel there'll be 105. And you add this up and you get 114 total ways. So the answer is 114 ways to win the game. All right, next slide. Oh, any questions? Oh yeah. Pascal's identity. Use the formula and alrighty. So I'm going to use the example to kind of explain it. Basically, it states that in combination K equals n minus 1 combination K minus 1 plus n minus 1 combination K. So for this example, it's drawn from the AOPS video for Pascal's identity. So I'm in this here. Down here. All right, so it was so basically the example in that video is Richard AOPS creator guy and his coworkers are making committees. And if you don't know what a committee is, it's like a group of people who make decisions. Okay, and basically there are 12 different people in total, and the committee has 3 people. So this committee has 3. And bad committees, basically, we're gonna make this called a bad committee. So a bad committee is one in which we have Richard in it. Okay, I'm not like dissing the creator of AAPS. Like this was his example. Bad committees are the ones where Richard's in it, and we're gonna use this one as bad. And the good ones are the ones where Richard's not in it. This one is good. Good. Oh, Richard. Okay. So for the bad committees, so it'll be n minus 1 over k minus 1, because if you look at this, we already have that Richard will be in the bad committee. So it's basically guaranteed that it'll be in there. So we have now 11 people to choose from. And now there's only 2 spots available because he's guaranteed to be in there. So we have the total, which would be in, is 12 combination 3. This equals 11 combination 2 plus, and we're just setting up the formula here to explain it. The question's not actually asking for anything specific, but it might ask for like a part plus n minus 1, which would be 11, because Richard, we know in the good committees, we know that he's not going to be there. So we don't even need to consider him in the equation. And then there's 3 spots here. So this is what we got set up. Now we can prove this. So 12 combination 3 is 220. Big brain, quick math. All right, 11 combination 2 is 55 plus 11 combination 3 is 165. If you add these, you get 220. Boom. Alright, but so it might ask for like a term, like it might say like it might say something like, let's say you have 8 people and you can choose 3 to be on a committee, but and there's already one case like laid out or something. Or like it might just say like, okay, no, yeah, okay, so there might be just be one case laid out, say already like the bad committee case, but you might have to find like the one that like fills in this spot. So yeah. And this is kind of like a basic version of these Pascal's identity and hockey stick identity, and some of our other problems in the thing will be much harder. Yeah, very hard. Okay, so and then we have reviewing practice. So here are our main ideas. Pascal's triangle is used for finding binomial coefficients. Binomial expansion is just different methods to quickly solve these expansions, and then hockey stick identity, a theorem that allows you to find number of ways to find like X out of Y things, kind of. And Pascal's identity, like while setting up an equation with 2 different cases or something. Yeah. And yeah, so Raymond's gonna send the practice to commit.
Okay.
Let me is this, oh yeah, okay, so it should look something like this. And well, let me just finish this here. So
Okay. Are we gonna do breakout rooms?
we can
It's
make
a
like
small group.
I think
I
we can
don't-
make like 2.
All right, I'll do that.
Okay, but just one more thing to look at. So this is like this is the easy question. We've like posted the answers for number 1. Okay, bye Darwin.
Bye, Alan.
I'm gonna stop the recording now.